This is a manifold. The pressure distribution is shown by the water levels in these manometer tubes. With the bleed valves closed, the average water velocity is the same at all cross sections, and there is a very slight pressure drop due to viscous forces. I'll reduce the volume flow at successive sections by bleeding water from the manifold. The pressure now rises. Since the area is constant, the velocity is proportional to the volume flow. Therefore, the velocity decreases. It is this streamwise deceleration which produces the streamwise rise in pressure. In an incompressible, steady, non-viscous flow, Euler's equation has a special integral called Bernoulli's integral. Along each streamline, the sum of the static pressure and the dynamic pressure is a constant. This sum is called the stagnation pressure. On any streamline where the velocity is high, the pressure is low, and vice versa. The highest possible pressure, the stagnation pressure, occurs where the velocity is zero. A very large reservoir supplying a flow to a duct system is itself a stagnation region. Here is a streaming flow past the blunt body with a central stream tube marked by hydrogen bubbles. The widening of this stream tube tells us that the flow is decelerating. The singular point where the central streamline reaches the nose is a stagnation point. The speed is zero there. On both sides of the unique stagnation streamline, the fluid decelerates, but not to zero speed, and then slides around the sides. The stagnation point is put to practical use in a pitot tube. The hole at the nose measures the stagnation pressure of the particular streamline reaching the hole. We've placed pitot tubes at the upstream and downstream cross-sections of the contraction, and these are the static pressure manometers we had before. The difference between the stagnation pressure and the static pressure is the local dynamic pressure. So this is a way of measuring velocity. Because of the area contraction, both the dynamic pressure and the static pressure change, but the sum of the two, the stagnation pressure, remains constant, which is what Bernoulli's integral told us. Bernoulli's integral also explains how we can produce suction by blowing. To show how a venturi can produce low pressure, we have formed half of a symmetrical venturi in this special test section that has one adjustable wall. A great many static pressure taps are in the straight wall and in the curved wall. Here it is set up for test. These are inclined manometer bores to show the pressure distributions on the two walls. We will observe the lengths of the water columns looking down from a position directly above. Now the flow is steady. We will look first at the pressure distribution on the straight wall. Continuity tells us that because of the area contraction, the velocity increases to the throat, and this causes a pressure drop. Downstream of the throat, the area increase produces a velocity decrease. and this causes the pressure to rise. At the upstream and downstream ends, where the cross-sectional areas are equal, the average velocities are also equal, and Bernoulli's integral would predict equal pressures. But the downstream pressure is actually somewhat less than the upstream pressure. This difference is due to viscous boundary layers, whose behavior we must always keep in mind, even when we pretend viscosity is absent. For instance, the area divergence here is much too rapid, and there is very little static pressure recovery in the diffuser. Far less than before. Even a very small amount of viscosity, if it leads to boundary layer separation, can produce very large changes from a truly non-viscous situation. In this experiment, water flows through a venturi that discharges to atmosphere. As we increase the flow, all pressure differences increase with the square of the velocity, and the pressure at the throat decreases. The gauge shows vacuum, and the pressure at the throat is now about 20 inches of mercury below atmospheric. Watch the throat. These patches that form are actually steam. This is cavitation. When the absolute pressure goes below the vapor pressure of about 1 inch of mercury, boiling occurs. The water changes to steam, and the subsequent collapse of the bubbles, which you can hear, creates enormous stresses in the wall. Mechanical stresses owing to the implosive collapse of cavitation bubbles on a surface do great damage to hydraulic machinery. And to marine propellers.